last speaker, who is Thomas Hocker. And the topic of his talk is assessing the effect of SOFC, microstructure on performance and degradation. So I hope you stay with us for the last talk and not too tired.
Thank you very much for the very nice invitation to this symposium. This collaborative work I'm going to present between our group, that's here the Institute of Computational Physics and Zurich University of Applied Science, which is a small engineering school. Then Hexes, formerly Sunde Hexes as an industrial partner, and Empower represented by Sunde. So, as a motivation, I think it's obvious to anybody here that the electrode microstructure has a key role both in the performance and in the degradation of SOFCs, which are of course of major concern. As you can see here, experimental data for nickel A, Y, and C anodes, where you have different microstructures. You have different electrode resistances right from the beginning, but also different types of degradation behavior. So, as we also saw today, there are extensive experimental investigations on this microstructure, but I think what is missing is our methods to link different experimental data to each other. I think this is the value of modeling. So when I started this work, that was about 2 or 3 years ago, I looked at I guess one of the most well-known electrode models, which is, was published by Paola Costamagna in '98. And it's a very nice model, but she uses analytical expressions to characterize the microstructure, which are based on coordination number and calculation models. And we soon found that those models lack some flexibility to include the characteristics in more detail as particle size distributions or different porosities. So the idea is to develop simulation tools which make those links between the electrode preparation, this is what you can change, then the electrode characteristics, that is what you analyze, and finally the performance and also the degradation behavior of your fuel cell, including current connection. And since we are working closely with this industrial partner, we have rather an engineering approach to it. So there are at all stages, I can say there's a lot of room for improvement, but nevertheless we try to do something where you actually get from a microstructure to the performance of a repeat unit. So we start with generating artificial microstructures here, for example, for a two-phase mixed conducting anode. Then we characterize this microstructure by finite element analysis. And here you also have a flexibility what you analyze here on this microstructure level. In the results I'm going to show today, we extract the effective electronic and ionic conductivities, as well as the, I should say this is here not the triple phase boundary length, the way this has been defined today, but this is the interface area between the two phases, which is in agreement with what has been done in the Costamagna paper. And then from that information, we move up to a continuum model, still finite element, but now you lose the microstructure information, it's all in your effective parameters, and you characterize your electrode. Let me see here, this is total resistance is here in blue curve, then the polarization resistance, the red curve, and the brown curve represents the ohmic resistance as a function of the nickel content of your electrode. And on this stage, we do not include the gas transport, but when we then take those values and put together a whole cell with all layers, then we also include gas transport. So this is then also a finite element model. So it's a continuum model. And then the final step would be to include non-homogeneous current collection, which is for practical purposes very important, because if you want to optimize your cell, so to say your thicknesses, you might get very different answers if the current cannot just flow in one direction from the triple phase boundary to the current collector, but has to go longer paths. So here you see the cell, and here you see parts of the current collectors, and you have to see here this is electronic potential distribution, so it's very homogeneous, and when this is here the ionic potential, and if we have a closer look, it is also quite inhomogeneous. So the way I set up my microstructure goes like this. I do not reconstruct a 3D microstructure from experimental data, but I define a particle size distribution for each phase. Right now I have 8 different sized cubic particles available, and I can give the overall volume fraction of the 2 phases. And then I use a random number generator to place those particles within a defined cube. And of course there's some arbitrariness to that. So I start out with placing the larger particles first. And this implies that the smaller particles later after, they have only a restricted room available, and therefore can also have some microscopic ordering, despite the fact that everything is done by a random number generator. So what is another parameter is the physical length of this grid here, and I'll talk about it later. So here you see how such an artificial, like a 2D cut through such an artificial microstructure looks like. So we have the force and flat, gray is nickel, and white is the 8YC. How do I get that? I start out with a continuous particle size distribution as I get it from Lorentz Holzer for a certain real electrode, and then I assume that my particles, my discrete particles, have the same PSD. So this is represented here for the nickel phase by this blue curve, the cumulative size distribution of it. Then so to say, I'm here still at the stage where I have my single particles. Now I kind of simulate my sintering process. I put them together to get my microstructure. Then I send these images back to Lorentz, and he analyzes them again with the same algorithm. And what he gets are those is this red curve here. So you see, it's not a perfect agreement. Also due to the fact that I'm rather coarse here in my particle size distribution, but for now it's close enough. And with this very simple approach, we can now track processes within our electrode, like nickel coursing here, and that's what I'm going to show in a couple of minutes. So for the extraction of effective parameters, we apply a potential to the electrode, and from that we extract the effective conductivities of the ionic and electronic phases. And I should also mention for the we also extract the interface between the 2 phases by running a current through the system and checking which particles are contributing to the current, and only those particles are accounted for when I calculate the overall interface area. Very short word to the software I'm using. It's an in-house tool. It's about 20 years old. It was developed at ETH in Zurich, and one of the main developers, he's a colleague of us, and he develops it further. It's not a commercial tool really, but it has an interface. So here you see this is kind of a programming editor with which you define your model, and then you have also some graphics capabilities. So for us it's a good tool to use, but I would say it's somehow in between a commercial tool like COMSOL and a purely research code. And so if you look at the electronic potential distribution of different electrodes, those are typical pictures. In a well-conducting electrode, you see you have basically those equipotential lines, so everything within the electrode is contributing to the transport. This is here an artifact, it's without particles. So when the conductivity gets poorer, you see that only certain parts of the electrode contribute, and in the worst case, when you fall below the percolation threshold, your electrode becomes inactive. And so if you look at how the effective conductivity changes with the nickel content, those are the typical curves here, also well known from the literature. Here you see an analytical model. Here you see the finite element calculations for different porosities for certain particle sizes. If you want to compare them directly with the experimental data, you need to know the microstructure. And this is often a problem to validate the model. So we looked a little bit into sinter nets. So if you have two particles here and they form a sinter neck, and of course this can have an effect on the transport of charges, and we wanted to investigate this a little bit further with cylindrical particles, where we can assume some constriction here, also with different shapes. And so those are typical results. So of course, I mean, it has to be in this way that when the sinter neck becomes small enough, then the complete potential drop happens over this neck, and it has a limiting effect. And you can then define an effective conductivity, which roughly goes with the diameter of this neck divided by the average particle diameter times the bulk conductivity. And this is a way it's a cheap way to include the sintering neck effect into the model. The way it goes then is that, and this is by the way the advantage of when you start with an individual, with the discrete particles in your simulation, then you keep this information, so you always know where the sinter neck has to be. Like you see here in this example, you have two nickel particles here and there, and then you have this interface region where you can reduce the effective conductivity to cheaply simulate the effect of sinter necks. And what it will do is it will give a penalty on smaller particles, which have of course many more connections than larger ones. Then here I'll go very briefly over that. It's about the effect of the nickel content on the porosity. Of course, if you have more nickel in your electrode and if you reduce it, then the porosity will increase. Here you see the theoretical curves with different starting porosities, so to say in the oxidized state of your electrode. And here you see some data. So in the reduced state you have for one type of electrode you have this curve, for another one you have this curve, and you see that only the trends are roughly correct, but it's again, you would need to know more details about the microstructure here to make a better comparison. But what is interesting, if you take into account that the porosity changes with nickel content, this has an effect on the interface area you calculate. So for equally sized particles, you get this bell-shaped curve, which is symmetric about nickel content of 0.5 in volume percent solids. So when you now include the porosity change with the nickel content, this means that this curve shifts to the left. What you see here is the percentage of nickel particles that contribute to the percolating network, and you see it's a strong function of the porosity. So porosity is a key parameter here. This is we'll also go very briefly only over it. This is a check if the values that we calculate for this interface area, if they make any sense. So if you look at the polarization resistance, which can be approximated here by this linearized version of the Butler-Volmer equation, if you know this value from impedance data, if you know the current exchange density, which we normally don't know, but let's say we get it from the literature, then you can solve this equation for the for this A triple phase or two-phase boundary, depending on how you define it. And it turns out when for the current exchange density, I used here values published by Holzer some time ago. He gives a value of 1,500 angstroms per meter squared at 950 degrees C. And it turns out that it gives a value of this interface area of 700,000, 1 over meter, which somehow corresponds well to what we calculate. And it's actually more than surprising, I must say. So, but it's the first check and needs further investigations. So here you see that when you now play around with your microstructure, let's say you start with this one here, microstructure 1, you get an effective conductivity for your nickel phase, which is quite high here, 180,000 siemens per meter. The experimental value in this case was 4 to 5 times lower. So you ask yourself, how can that be? Well, if you make some modifications to your microstructure, then you see that this value can drop quite dramatically, even though the modifications are not that large. So the porosity definitely has an effect. So if you get it wrong by 10%, this leads to a big drop in this effective conductivity. So this is perhaps one of the most important slides. Here you see how the overall, it's the overall resistance of a nickel 8YC anode, how it changes with the microstructure. So the experimental data is given here in orange, and this column here and the red one, as well as the blue markers here, indicate simulation results. So you see in all cases the trends are always correct. But of course you have the current exchange density as a kind of free parameter, and also when you, like, those are the latest results I got, where I used the microstructure continuous particle size distributions as obtained by Lorentz, and you see for those 3 cases here, going from a fine to a coarse electrode, they agree surprisingly well with the experimental data. So another issue is that what do small quantities of small particles, what do they do? You see here the polarization resistance of an electrode, and how again small changes in the microstructure make quite a big shift here in the resistance value. But overall, the values are pretty close to the experimental results anyway. Here, somehow similar to what you have shown, it's about nickel coarsening. So when you go here from this blue curve to the green curve, and you look here at the effective nickel conductivity, you see that it drops quite drastically with an increase in the nickel particle size. What goes along with it, that the probability or that the number of nickel particles belonging to the percolating network drops also. And this is, I guess, a nice agreement what you have shown. This then leads here to a very sharp increase in the ohmic resistance. So you see here the polarization resistance, which also changes. So the overall level increases when you get coarser particles. Makes sense because then the triple phase boundary decreases. But what really kills your electrode is this sharp increase in the ohmic resistance at the percolation limit. How much time is it? Okay. So here you see some results from this full cell model. So you see in red, this is here the electric current. So it's a bit cumbersome because those are here negative values. So you see that within the electrolyte you have no electronic conductivity, and then it increases here. So this is here the anode side, then you have two different anodes, one let's say catalyst layer, anode 1, and one current connection layer, anode 2. So you see that within your mixed conducting electrodes, how the electrical current increases, and similarly, due to the conservation of charges, the ionic current then drops here to 0, and the ionic current stays constant here within the electrolyte. We use the Lowry-Butler-Volmer equation to model the charge transfer, and yes, this is certainly not perfect. It's more investigations, but for now, let's. We wanted really to focus on microstructure and keep everything rather simple. So, referring to what I said at the beginning, if you now do this, including this non-homogeneous current collection, what you observe is that you can pay a rather large penalty for that, and this we call here some geometric resistance. And in this case here, it's at the order of 150 milliohm centimeters squared, compared to a cell that would be ideally contacted. So for the people or companies developing fuel cell stacks, obviously this is an issue, and it's also an issue how thick you make your cell layers. So let me conclude. So I didn't mention this, but there's a review paper by Sunde on electrode modeling, but also on electrode phenomena. And I compared this review paper, he makes, I think, 10 points or so, where he gives the main characteristics, and I checked that, and I would say that the model I presented exhibits all the features he shows in a qualitative way, at least. However, there's some arbitrariness in that. The particles I have are cubes. This is first of all a limitation. Also the way they can contact with each other. Of course, it's not like in reality, so the cubes are all nicely aligned. There are some ways to overcome that, at least partially, for example, by introducing some effective conductivities at the interfaces between those cubes to account for synter necks. But Yes, this is the beginning, and there's certainly much more work that needs to be done on that. So, what are possible extensions? You can now go ahead and, for example, simulate the gas transport within the pores instead of using the continuum model approach. This, of course, should be done, but it's clear that the model and the simulation times will largely increase. Also, the charge transfer here, you have different possibilities and should be exploited. We also want to go to single-phase mixed ionic electronic conductors to see what the results are there. And in order to generate the microstructure, it's also possible, and I think you made also a reference to that you can, for example, also simulate the sintering process. That's an interesting approach. And yes, what we have not done right now is taking the microstructure as it comes from image analysis, simply because the simulation times will be much higher than, I should say, for a single run of the experiments you've seen here, it takes between a minute and perhaps 15 minutes. Then, in order to get a good average value, I use between 15 and 30 different configurations. It's well agreed with what you have reported. So this gives you a fast tool to make geometric optimizations. Thank you very much for your attention.
Thank you very much, Thomas. There's still some people awake to ask some questions, I hope so.
I'm Nigel Brown at Imperial College. Can I just ask then, am I right in thinking that you assume that the whole electrode volume is equally active in your extraction?
Yes, this has been assumed, yes.
I just wonder if you, I mean, obviously we and others have shown that it's actually going to vary depending on the open potential. I just wondered if how you thought you might address that going forward.
Well, in this case, if you use the random number generator to set up your microstructure, obviously at each point you get the same. So if you extract some effective coefficients from that, then they will also be the same. But it's obvious that this is not the case. Lawrence also showed these different zones that the nickel content and the particle size distributions vary. So this would be a logical next step.
I have one question. Have you considered actually including the electrolyte interface? This would simply add one extra row of voxels.
No, but this, of course, this is the nice thing about this finite element approach. I mean, geometrically, you have a lot of flexibility, and that's the big drawback with those analytical models you find. Yes, if you want to add something like that, it's a rather cheap thing to do.
Okay. Are there any questions? Yes.
Please show the current, ionic current and electric current distribution. It seemed somewhat symmetrical. So I was wondering.
Okay, this is a good point. In this calculation, I use identical parameters for the cathode and for the anode.
I mean,
and it's also, you have to remember, this is not an anode-supported cell. It's an electrolyte-supported cell at a very high temperature. So the polarization resistances are usually between, I don't know, 30 and 60 milliohm centimeters squared. But here, I'm sure I used identical parameters on the cathode and on the anode side.
I mean, each of the electrodes, I mean, if there is a large difference between the conductivities of ions and electrons,
yes,
there should be a symmetry of the potential difference, because normally we have large potential drop in the ionic phase. So if you get far away from the electrolyte or electrode surface, potential get decreased.
Yes.
And that will make the the electronic and ionic current distribution somewhat more shifted to the.
Yes, it's not shown here, but I used to also get some results that if a current decrease or increase, which is more like I don't know, the exponential time.
Yeah.
Yes.
Do we have any more questions? It's not the case, so let's thank you, Thomas.